Today we're going to talk about average and instantaneous slope. Now we know the formula for the slope of a line, and we're going to be using that formula today. It's going to be y2 minus y1 over x2 minus x1. That we can use to find the average rate of change between any 2 points. So if I have a graph, f of x is x cubed minus x, the graph looks like the curve. And if I choose 2 points on that graph, I'm choosing 1, 0, and 324. Now 324 is way up there, but we're just going to use this point just so you can see a point. If I want to find the average rate of change between those 2 points on this function, it's basically using the slope formula. So in function notation, instead of y2 minus y1, we would have in this case, f of 3 minus f of 1 all over 3 minus 1. F of 3 is the y value. F of 3 is going to be 24. F of 1 is 0. And so you just substitute into the formula 24. The slope is 24 minus 0 over 3 minus 1. So that ends up being 24 over 2. And that slope is going to be 12 over 1. And if you look at the graph and think about the graph, we want a pretty steep positive slope. And 12 over 1 would definitely be that. So to define the average rate of change of f of x over a given interval, x1 and x2, it's the slope formula in function notation. So the average rate of change is just f of x2 minus f of x1 all over x2 minus x1. And it's the slope of a line between 2 points. What we will do in class is calculate the average rate of change for a function f of x, which is 2 times e to the x over this interval, -1 and 2. But from here on out, we're going to talk about the instantaneous rate of change. So the average rate of change provides us with an approximate answer because you're only looking at 2 specific points on a curve. Let's say I have a curve that looks like that, and I want to find the average rate of change between this point and this point. Well, that's not going to be very accurate. That really tells me nothing about the graph whatsoever. So that's not a very useful calculation for us. What we want to do instead is come up with a way to find the slope of a line instantaneously. We want something called the instantaneous rate of change. And that is pretty much evaluating the slope of a curve at a single point. So we're going to start with the formula for average rate of change. And I'm going to show this here, then I'm going to show you with some dynamic software in the class so you can kind of see things, how things move and how things get derived. But here is our average rate of change formula, f of x2 minus f of x1 all over x2 minus x1. So if I have a graph, and let's just use a basic function, let's say just something that looks kind of parabolic. Okay, it passes a vertical line test as some kind of a function, so this is f of x. And I start at a certain point. So I'm going to label this point. My x value there I'm going to label c. And I'll start with the average rate of change, so I'm going to put a second point on the graph. First point I'm going to label A, second point I'm going to label B. And I need a second x value down here. Now, instead of just putting another random number on here, or letter, I'm going to relate it back to C. And basically, I'm going to call the difference between C, which is my first value, and the second value, I'm going to call that H. And this is standard notation that you're going to see in just about every pre-calculus and calculus textbook. So the spacing between my first x value and my second x value is h. So I can actually call that second value, I can write it in terms of c and h because it's going to be c plus h. So if I think of my coordinates, point A is going to be at an x value of c and a y value of f of c. And point B is going to have an x value of c plus h, if I can squish it in here, and a y value of f of c plus h. Let me write that better because you can't really see it. So point B, again, is going to have, I'm going to write it down here, c plus h and f of c plus h. That's that point. Well, here's what will happen. That's the average rate of change between those 2 points. Okay? So if I start with that formula and calculate the average rate of change, it looks like this. My second value, my second y value, is going to be f of c plus h. So it's f of c plus h minus f of c over c plus h minus c. So let me write that out and we can see what that looks like. The average slope is f of c plus h minus f of c. Those are my y values. All over c plus h minus c. Well, what's going to happen? How does that simplify? If you look at this, my c values here are going to add to 0. So I'm left with a function that looks like this, f of c plus h minus f of c all over h. Now, here's the deal. What I really want is to take this point B and to move it closer and closer and closer to A until they're pretty much the same value, because the instantaneous slope is the slope of the line that's pretty much going to be tangent at point A. So that's what I really want. So as I move this point closer and closer and closer to A, what's happening to the value of h? And if you think about it, the closer I move this point to A, the smaller the h value is going to be, because the y value here keeps getting closer and closer and closer to c. Eventually, what we really want is for h to be 0. But I can't evaluate this fraction when h is 0. It's undefined. This is where the idea of a limit comes in. So in order to evaluate this thing, I want to know what's happening as h approaches 0. So as point B approaches point A, h is approaching 0. And that is how we are going to define the instantaneous slope of a function. So here it is, the instantaneous rate of change, or the instantaneous slope, as x when x is equal to c. So we're talking about a single point now, not 2 points. A single point is given by the limit as h approaches 0 of f of c plus h minus f of c all over h. So this is the key right here. I don't care what's happening right at when h is 0, but I can evaluate the limit as h approaches 0. So that's what we're going to do. I'm going to give you some steps and we're going to work through an example and then look at it more closely in class. So calculating the instantaneous slope at a specific point, so x is equal to c, some number c. Here's what you do. First, you got to calculate f of c. And that's going to be a numerical value. So you need a numerical value for that, f of c. And then you need to evaluate the expression. You need to evaluate and simplify f of c plus h. C is a number, but h is a variable. Most of the work will be in simplifying f of c plus h. And then you evaluate the limit. You evaluate the limit as h approaches 0 of f of c plus h minus f of c all over h. So that's what we're going to do next in an example. Alright, the example I'm going to work says find the slope of the line tangent to f of x is equal to x squared at x is equal to 5. So I'm trying to find the instantaneous slope, and that creates a tangent line. So when x is equal to 5, that means c is 5. C is a value of 5. So what I first have to do is find f of 5. I need to find the corresponding y value when c is 5. So f of 5 is going to be 5 squared, which is 25. So I have a coordinate point, 5, 25. That's where I want to find the slope. Okay? The next step is I have to evaluate f of 5 plus h. That's an algebraic expression. 5 plus h squared. I need to multiply that out. If it's cubed, I still need to multiply it out. If I'm mean enough to give you something to the 4th power, you still have to multiply it out. So this is 5 plus h times 5 plus h, 25 plus 10h plus h squared. So now I'm going to put that in my formula. I'm going to evaluate the limit. Here's the limit. As h approaches 0 of f of 5 plus h minus f of 5 all over h. F of 5 plus h is 25 plus 10h plus h squared. F of 5 is 25 all over h. Here's what's going to happen. Here is what always will happen if you do your algebra correctly. Anything that does not have an h in it is going to subtract away, leaving you the ability to reduce the h down in the denominator, so I don't have an undefined value anymore. So when I look at this, my 25 and my minus 25, they're going to add to 0. So now I'm evaluating the limit as h approaches 0 of 10h plus h squared all over h. My h is going to reduce to 1. This guy is going to reduce to 10. This guy is going to reduce to h. So now I'm evaluating the limit as h approaches 0 of 10 plus h. Well, now I can just directly substitute in, because that's like evaluating a polynomial function. When h is 0, my answer is 10. So the slope of the line tangent to f of x, when my function is x squared and x is 5, the slope of the tangent line is going to be 10. So we'll go over this again in class and work some more examples. This process is algebraically intensive, but the actual kind of math calculus part of it should be fairly simple once you get the steps down.